Welcome to the second Tractography lecture. My name is Michiel Cotard. So in this lecture we will look at how to estimate the fiber orientations within each voxel in the brain using the FSL tool BEDPOSTX. And in the next lecture we will see how PropTrackX can put those fiber orientations together to do actual tractography and reconstruct the major white matter fiber bundles in the brain. So we already saw an example of tractography using the diffusion tensor. So in this talk, we'll look at what the limitations of this diffusion tensor tractography are and how we can use BEDPOSTX to go beyond what we can get from the diffusion tensor. The main limitation is that the diffusion tensor can estimate in every voxel at most only one fiber orientation, which is because it only has one first eigenvector of the diffusion tensor, this preferred direction of diffusion. But if, for example, we look at this voxel here, so the red square here in both images are the same voxel, then we can see that in this voxel we have both the corticospinal tract running from bottom to top, as well as the superior longitudinal fasciculus running from back to front. And so if we wanted to fully reconstruct both of these white matter bundles, we would need not just a single estimation of orientation within the voxel, but we would need two fiber orientations, one corresponding to the corticospinal tract and one corresponding to the superior longitudinal fasciculus. So let's actually look what the signal looks like for such a voxel where we have multiple fiber orientations. Well, let's first look again at a single fiber orientation. So in the upper left, the black line indicates this single fiber orientation, and the red disk essentially shows the signal which we would expect given that single fiber orientation. So we have very little signal if the gradient is aligned with the fiber orientation, because in that direction there's a lot of diffusion and hence a lot of signal loss, while we have a lot of signal perpendicular to the fiber orientation. And this situation is actually well described by the diffusion tensor, which gets this cigar shape shown in the lower left with a clear preferred direction of diffusion, and it fits the data quite well. However, if we get multiple crossing fibers, such as here we have two fiber orientation, then the diffusion tensor cannot fully capture all of this information, and you just get this flat pancake-like shape, often called an oblate tensor. And in the lower right, we can see that this doesn't actually fit the data that well. And that's actually good news, because that means there's more information in the diffusion MRI data than captured by the diffusion tensor, and hopefully we can use this extra information to extract the individual fiber orientations. Things become even worse for free fiber orientation, where the diffusion tensor doesn't have any preferred direction of diffusion at all anymore, but we still see that there does seem to be some extra information in the measurements which is not captured by the diffusion tensor. And so all of these different diffusion tensors are present in different parts of the brain's white matter. For example, in the corpus callosum, connecting the left and the right hemisphere, we tend to have this preferred direction of diffusion from left to right with this clear cigar-shaped prolate tensor, while in other parts of the brain we've got crossing fibers leading to oblate or even spherical tensors. In addition to capturing multiple fiber orientations, what we would also like to quantify is the uncertainty on these fiber orientations. After all, as shown in this work by Derek Jones, if you gather from the same brain the same diffusion MRI data multiple times and recompute the diffusion tensor every time, you'll get different results just due to random noise. And this plot shows the variability in this first eigenvector of the diffusion tensor, which we would use in diffusion tensor tractography. And in regions like the corpus callosum, all of these individual estimates are very much aligned with each other, but in other areas like the gray matter or CSF or regions with crossing fibers, there tends to be a lot of variability in this first eigenvector between different data sets, which means that even if we acquire diffusion data in the same subject, the diffusion tractography through these regions would be completely different every time we reacquire the data. Of course, this noise is somewhat unavoidable, but we would at least want to be able to quantify what the uncertainty in our tractography is due to the measurement noise. And that is the second goal that we have in BEDPOSTX, and when we estimate the fiber orientations with FSL's BEDPOSTX. So, how do we do this? Well, first let's look at how we estimate multiple fiber orientations. And we do this by moving away from the diffusion tensor model and adopting a ball and stick model. So in the diffusion tensor model, what we assumed is that we have water within every voxel which has Gaussian diffusion, which might have some anisotropy to it. The ball and stick model is somewhat different in that we now assume that there's different compartments of water within each voxel, and in some of those compartments, specifically in the water within the axons, we assume that the water only diffuses in the direction of the axons and not at all perpendicular to it. This is the so-called stick compartment. And in addition to that, we assume that there's different water within the voxel outside of the axons, which doesn't have any preferred direction of diffusion at all. So this is outside of the cells or in glia cells or stuff like that. And for this water, we assume that the diffusion is equal in all directions, so it's isotropic. This is the so-called ball compartment. So our final signal will be given by the signal of this ball plus the stick compartment, and the equation for that is shown here at the bottom, where Sj is the measured signal for a given B value and gradient orientation, and Bj and Xj are that B value and gradient orientation. The things that we want to estimate are here in red. So from what we basically have, we have a sum of two terms corresponding to the ball on the left and the stick on the right. So for the ball of the left, we simply have that the attenuation of the signal due to diffusion is this exponent of minus the b times the diffusivity. So this is essentially the same as the diffusion tensor, but assuming that we have isotropic diffusion, so we just have a single diffusivity value here. On the right, we have a very similar equation, but this is for the stick. So in this case, we only have diffusion in one direction. So in addition to have as minus BD in the exponent, we also have to multiply with how well the gradient orientation is aligned with the fiber orientation. So that's a dot product here between x and nu squared. In addition to this, we also have to model how much water there is in the stick, which is given by the F, and the final variable is S0, which is the signal in our reference image. This was our B0 image, which was the image where we didn't have any diffusion weighting at all. And so anything within the square brackets gives how much the signal is reduced to the diffusion in on the left the ball and on the right the stick. Now, this still only gives us a single fiber orientation, which is the orientation that we estimate for the stick, which is given here in the equation as nu. However, we can easily extend the ball and stick model by considering multiple sticks. So in that case, in this case, our equation changes slightly. Now instead, we have a sum over multiple sticks, each with a different volume fraction, Fn, and each with a different fiber orientation, mu n. And this allows us to estimate more than a single fiber orientation in every voxel. So again, Sj, grade B value, and gradient orientation are known, and we estimate the volume fractions of all of the sticks. Any remaining water is within the ball. We estimate the diffusivity and the individual fiber orientations. So if we do this for the simulation, so the simulated data we saw earlier, then we saw that the diffusion tensor provided a poor fit to the data, but the ball and stick model provides a much better fit, which allows us to estimate the correct fiber orientation within these simulated voxels. Now, in addition to estimating the multiple fiber orientations, we wanted the uncertainty on each fiber orientation. And the technique that we used for that is a form often used in Bayesian modeling, which is a Markov chain Monte Carlo. I won't go into much technical detail in how Markov chain Monte Carlo works, but the very basic idea is that we start with some guess of what the fiber orientation and the diffusivity and all the other parameters that we saw in the previous slides, what those parameters are, and then we compute the model predicted signal, which we compare with the measured signal. And then we make a slight change to one of the parameters. For example, here between the first and the second row, we change the stick volume fraction. And then we compare again the model predicted signal with the measured signal. And if it becomes significantly worse, like in this case, we reject this step. If it's still consistent with the data, then we allow the change. In this case, we reject it, so we change something else. In this case, the fiber orientation. This still led to a decent fit to the data, so this change was allowed. And we just keep doing this, changing one parameter at a time, seeing whether we are still consistent with the measured signal. And if we do this often enough, this typically has to be done thousands of times, what you will get is not just a single best fit estimate of the parameters, but you will basically get a distribution for all possible values that are consistent with the measured signal. So in this case, what we are interested in is that we get all possible fiber orientations that are consistent with the measured signal. So what this looks like is basically a whole range of different fiber orientations, as well as different diffusivities and volume fractions. And putting together all of these fiber orientations, we get an estimate of how uncertain the fiber orientation is within each voxel from a single diffusion MRI data set, so without having to reacquire our data. So in the white matter on the lower left, we can see that these fiber orientation estimates are often closely aligned with each other, indicating that there's very little uncertainty in the fiber orientation, while in gray matter or CSF, there's much more uncertainty in the fiber orientation, which is reflected in our result from the Markov chain Monte Carlo by having a much wider spread in the estimated fiber orientations. So typically from this Markov chain Monte Carlo, we will take 50 samples of possible fiber orientations consistent with the data. Now, we've seen how we can estimate multiple fiber orientations by having multiple sticks in addition to the ball which we fit to the data. And we saw very briefly how we can get estimates of the uncertainty on these parameters by using a Markov chain Monte Carlo algorithm. However, this doesn't fully solve our problem yet, because we still have to determine within each voxel how many fibers are actually crossing each other. If we have a voxel in the corpus callosum, we will typically expect only a single fiber orientation running left to right, while in different parts of the brain where we have crossing fibers, we might want to estimate 2 or even 3 fiber orientations. So we need some automatic way to determine, based on the diffusion data itself, how many fiber orientations should we estimate within each voxel. And the technique that we use for that is called automatic relevance determination, or ARD. And the basic idea is here that we only estimate multiple fiber orientations if there's evidence within the data for the existence of those multiple fiber orientations. Mathematically, what we do is we add to our Bayesian analysis in a Markov chain Monte Carlo, we add a prior belief to the second and third volume fraction that these volume fractions are very small. Essentially, we say that we think they are very close to 0. Now, If we are in a voxel, such as the one shown here on the upper right, where our measured signal is well fitted by a model which contains only a single stick, then our prior belief that the second volume fraction is very small will take over, and so the second volume fraction will go to 0. On the other hand, if we're in a voxel which is poorly fitted by just a single fiber orientation and much better fitted by two fiber orientations, as shown on the bottom, then that need to fit the data well will override our prior belief that the second volume fraction is small, and so it will actually be some finite number, and we will estimate fiber orientations for both the first and second fiber orientation. So here it's just illustrating where our single stick model deviates from the measured signal, and for which we need a second fiber orientation. So what we then get from BEDPOSTX is basically not just a single fiber orientations like we got from the diffusion tensor, but we get 3 different fiber orientations, at least up to 3. You can personally select a lower maximum of 2 or even 1 if you want. And for each of these sticks, you get an individual fiber orientation as well as a volume fraction. So this is illustrated here at the bottom, where the underlying gray map shows the volume fraction and the red, respectively blue or purple lines show the estimated fiber orientation. Now, what we can see is that we basically, throughout the white matter, we do estimate a first fiber orientation, but for the second and third fiber orientation, you can see that parts of the white matter are missing. For the second fiber orientation, you can see that the corpus callosum has disappeared. This indicates that for the corpus callosum, a single fiber orientation was enough to fit the diffusion MRI signal, and so the volume fraction of the second stick was made low due to the ARD. In the third stick, we see that throughout most of the white matter, the ARD has kicked in, lowering the volume fraction, and only in a few places do we actually estimate the third fiber orientation. And now we can put together all of these images, but before we do that, we actually have to threshold based on the volume fraction, so we get rid of all the fiber orientations which were estimated for voxels where the ARD says that that fiber orientation doesn't actually exist. So usually we put a threshold of 5% to exclude these sticks with a tiny volume fraction. And if we do that, we can overlay all of these maps, and we get a map which looks like this, where if we zoom in on the centrum semiovalle, where we have multiple fibers crossing each other, you can see that we have some voxels with only a single fiber orientations, while in other voxels we needed multiple fiber orientations to fit the signal, and so we estimate 2 or even 3 fiber orientations. And this gives us much more information than the diffusion tensor to follow the white matter fiber bundles through these crossing fiber regions. This plot is just to illustrate on the right that these crossing fiber orientations are actually coherently oriented with each other, indicating that they actually represent real tracks and are not just fits to the noise. So, after discussing how BEDPOSTX estimates fiber orientations, I would like to take a step back and talk again about the acquisition of diffusion MRI data and how we can optimize this to get the best estimate of the fiber orientations. So as you might remember from the previous talk, one of the main variables we had to select when acquiring diffusion MRI data is at which B value do we acquire data. So the B value quantified how sensitive we are to the diffusion in the direction of the gradient orientation. Now, to estimate multiple fiber orientations, what we would like is to have a very high B value. And the reason for that is that at a higher B value, we are more sensitive to small deviations between the gradient orientation and the fiber orientation, leading to much sharper signal profiles at higher B values, as illustrated here at the top. And this allows us more precise estimate of the fiber orientations. It's often said that the higher B values give us more angular contrast. We have more signal difference in signal between similar gradient orientations. On the other hand, at a higher B value, we have the disadvantage that we have less signal left in total, which means that we will have a lower SNR. So there's a trade-off here. We want to go to high B values so that we can distinguish the multiple crossing fiber orientations, but we don't want to go to such a high B value that we get a very low SNR. And it turns out that actually what is the most optimum way to do is not just to select a single B value and just require a lot of gradient orientations at that B value, but to actually require the diffusion data across multiple B values. So this is referred as multi-shell diffusion data. And this at the bottom just shows that for the same acquisition time that we get more robust crossing fibers for multi-shell data compared with if we just select a single optimized B value. One thing to keep in mind is that BEDPOSTX, that the balance stick model in BEDPOSTX for the multi-shell data, when you have more than a single B value, needs to be slightly adjusted to fit well across the multi-B values. I'll not get into how this actual model is adjusted here, but the point is just that when you actually run BEDPOSTX, there are flags you can give to the model. And basically model equals 1 should be used if you only have single shell data, so one B value as well as B naughts, while model 2 or 3 should be used if you have multiple B values. In either case, what you will get is these multiple fiber orientations within each voxel together with the uncertainty. Now, unfortunately, this Markov chain Monte Carlo will take a long time. So on big data sets, this can cost days. There is also a version of this which will run on the GPU, so on the graphics card. And if your university has this available, this is highly recommended because it's hundreds of times faster, allowing something which would take days on a normal computer to actually be able to be calculated in less than an hour. Thank you for all your attention. And next time we will look at how we take these multiple fiber orientations and put them together to actually reconstruct the white matter tracts within the brain.